Have you ever stopped to wonder what's really powering the core of our internet and all our communication systems? I mean, how do you even build a network router or a massive messaging platform that has to handle millions of connections at once and absolutely positively cannot fail? Well, a huge part of the answer lies in a language and a set of ideas called Erlang/OTP. And today, we're going to break down exactly why its unique design is pretty much a perfect match for these incredibly important systems.
All right, so here's our game plan. We're going to kick things off with the core problem, what we're calling the concurrency conundrum. Then, we'll get into Erlang's secret weapon, the process. From there, we'll look at the OTP safety net that makes these systems so resilient. We'll connect all that directly to routing, and finally, we'll talk about the promise of building something that is just unbelievably stable.
Okay, so first things first, let's talk about the fundamental challenge here. When you're building a system that's doing millions of things at the same time, like a router directing all that internet traffic, you are smack in the middle of a concurrency nightmare. And in that kind of environment, things going wrong isn't an if, it's a when. The real trick is stopping one small failure from turning into a total catastrophe.
And this right here is the million-dollar question. Seriously, if you've got a system handling, say, 1 million different user connections, and a tiny bug causes the code for just one of those connections to crash, how do you guarantee it doesn't corrupt everything for everybody else and just bring the whole system down? So this really frames the two competing philosophies. On the left, you've got the traditional way of doing things with threads. They all live in the same memory space. Now, this is fast, but it's also incredibly fragile. If one thread crashes while it's writing to memory, it can poison the well for every other thread. It's like one domino falling and taking the entire set with it. But then you look at Erlang's model on the right. It's built on a really simple but powerful idea: share nothing. Every little task runs in its own tiny, isolated bubble.
So let's talk about that new paradigm. The absolute secret sauce to Erlang's whole approach is this concept of a process. But I want you to forget everything you think you know about processes or threads from your operating system. These are a completely different beast, way lighter.
An Erlang process is the basic unit of work. They are unbelievably lightweight. I'm talking millions of them running on a single machine. They're super fast to create and destroy, and, here's the most important part, they're completely isolated. They share zero memory. The only way they can talk to each other is by sending messages, kind of like passing notes in class.
And you know, this isn't some feature that was tacked on later. Erlang was literally built from the ground up for this. It was invented at Ericsson to build telephone switches, systems that had to handle tons of calls at once and could never, ever go down.
So how does this message passing actually work? Well, it's beautifully simple, and crucially, it's asynchronous. Process A just packages up a message and sends it to Process B's unique address. And the key is right there in step 2. Process A doesn't wait around for a reply. It just fires off the message and gets right back to work. Meanwhile, Process B has its own little mailbox. When it's ready, it'll check its mail, grab the message, and deal with it. This whole fire and forget thing is what prevents the system from getting bogged down.
Okay, so process isolation is fantastic for containing a failure. But what happens when a process actually fails? You can't just let it die and vanish, right? Well, that's where the second piece of this amazing puzzle comes in. The OTP framework, and its most famous idea, the supervision tree. A supervision tree is pretty much exactly what it sounds like. It's an org chart for your processes. You have worker processes that do the actual work, managing one network connection, and then you have supervisor processes whose only job in life is to watch over those workers. If a worker messes up for any reason, the supervisor's job is to step in and fix it. And you can build these trees as deep as you want. You might have a big boss supervisor watching over other supervisors, and each of those is in charge of a pool of workers. But the real magic is in those last 2 points. When a worker at the very bottom fails, only its direct boss gets notified. The problem is completely contained. The other workers, the other supervisors, they have no idea anything ever went wrong. The whole system just keeps humming along. This whole structure leads to one of the most famous and maybe counterintuitive philosophies in all of software. Let it crash. I know it sounds crazy, but it's actually genius. Instead of trying to write tons of complex, defensive code to handle every possible error you can imagine inside a worker, you just don't. You write simple, clean code. And if something totally unexpected happens, you don't try to recover, you just let the process crash cleanly. Why? Because you've got this incredible fault tolerance loop baked right into the system's DNA.
So a worker hits a bug and dies. Its supervisor gets the memo, and its predefined strategy kicks in. And most of the time, that strategy is super simple. Just restart it. So it spins up a brand new squeaky clean version of that worker, and the system heals itself automatically. We're talking microseconds, all without any other part of the app even noticing.
Okay, so we have these really powerful concepts, right? Lightweight, isolated processes, asynchronous messages, and these self-healing supervision trees. Now, let's connect the dots and see how this becomes the perfect architecture for the world of high-performance routers and decision systems.
This is where it all just clicks into place. Look at this. Every single major challenge a router faces has a direct, elegant answer in the Erlang/OTP model. You need to handle millions of connections? Lightweight processes were born for that. You have to make sure one bad connection doesn't take down the whole ship? That's process isolation by design. The need to recover from problems automatically? That's what supervision trees do. And that constant demand for high availability? That's the beautiful guarantee you get from the let it crash philosophy. It's a perfect match. So here's the bottom line. The architecture lets you create a perfect one-to-one mapping. You spin up one tiny, supervised Erlang process for every single network connection or every single user session. So if a weird bug, a network glitch, or some bad data causes that one process to fail, it crashes, its supervisor restarts it, and the other 999,999 connections just keep going, completely uninterrupted.
And that brings us to our final, and honestly most important takeaway. It's the ultimate promise that this entire way of thinking makes to anyone building these kinds of systems.
This is the formula. It's not magic, it's just brilliant engineering. Isolation stops errors from spreading like a virus, and supervision gives you a built-in automatic recovery plan. Put those two together, and you get a system that isn't just tough, it's predictable. You actually know exactly how it's going to behave when a small part of it fails, because that failure is a core part of the design, not an afterthought.
At the end of the day, this isn't just a bunch of clever hacks. It's a formal, consistent way to build reliable software. OTP gives you the rulebook, the patterns, to make sure that every single part of your system, from the tiniest worker to the very top, is built on these same principles of fault tolerance.
So, I'll just leave you with this question to think about. We've been focused on routers, but this model applies anywhere you need extreme reliability. Think about financial trading platforms, massive IoT data systems, global-scale chat apps. When you can build your entire system on the assumption that small failures are normal, isolated, and automatically healed, it just completely changes the game. It lets you build systems that are, for all practical purposes, truly unbreakable.